So I will give. I present 3 challenges with solutions. I will give a bird's eye overview, and then maybe we can be adaptive. So please shout out in your questions, and we can zoom in on details. But in this slide, if I can reload. Okay, the animation is not playing.
Movie?
Yes, so this is a movie. So how can I reload here? No, thank you very much. So this almost gives a bird's eye view of everything. So I think this is the most important slide. So I will come back to the 3 challenges, but I think maybe this connected to CFD, this is the most important challenge, I think. So you could say today the industry does not trust aerodynamic simulation, and this is posed as a grand challenge problem by NASA Vision 2030. But we have simply gone back to Euler proposed in the 1700s that, here is fluid dynamics, this should predict most sort of phenomena in nature. So we went back to Euler, and over a period of about 15 years, we got initial promising results, and now we've validated this at the most sort of advanced level in the world for, let's say, 15 years. So now we see Euler works very well. So this is sort of opens up enormous new possibilities. So here is the high lift prediction benchmark. So we predict the separation, which is the main challenging mechanism. And we get very good sort of detailed pressure validation. So that was the challenge. And what this contains, it makes it very simple. So it's first principles. So it's direct simulation of natural laws. So there are no sort of modeling parameters, no turbulence modeling. And so it's a free slip condition, 0 friction. And one consequence is also that it makes CFD extremely fast and cheap. So about 100 times faster and cheaper than the cheap industry standard runs, and about 1,000 to 10,000 times cheaper than the sort of advanced simulations that are done in industry and academia, like LES type of simulations. So this simulation can even be done on, let's say, 1 core, let's say in 2 days. So we showcase this even in like a Jupyter notebook. You can run this on free resources. So this opens. So now we're working with Saab in Sweden in industrial applications. So this is a Saab open research model. And it's both incompressible and compressible. Here is in the incompressible setting. So that's fantastic. And it's also, if you think CFD is challenging, it's sort of, it's just sort of conservation of momentum, F equals to ma, right? And then it's a very general automated stabilized method. And that's it. That's all you have to do. So I'm very happy to help you with that. And it means you can now reliably design, optimize, certify, and innovate aircraft, engineering systems, and so on. So this is what we are pushing now with the aerospace industry. It's also reproducible, so I can get back to this. And we deliver it as a sort of a pedagogic breakthrough also, so we can get back to that. And a recent, you could say, breakthrough development also with aeroelasticity. So this is a adaptive Euler fluid structure interaction. So here the whole aircraft is also elastic. So then we can reproduce, it's called a buffet phenomenon, so sort of an oscillating pressure field on the wing. And we've been highlighted in one of these NASA workshops by the branch chief of aerodynamics at NASA, Chetin Kiris. So sort of a positive supporting public peer review by NASA. Sort of this should be explored further, and it's good. And some success stories. So we're elected to the 100 list in Sweden, and also this pedagogical breakthrough. So this is, we are being highlighted by as a possible solution to the crisis in math and STEM, and also our advanced version of the DigiMat online course has had over 30,000 participants, the largest online course in Sweden. So this sort of that it's simple and fun, I think that's something I want to showcase also. So please join the fun and do sort of play with simulations in FEniCS. So now I'll just go through the 3 problems on a sort of bird's eye view, and then we can zoom in into details. So this is what I presented, Adaptive Euler. But also, and this has been exacerbated even more now. So you will think sort of in academia that people are doing sort of what they are honest sort of and what do you say, systematic and so on. But that does not seem to be the case. So many research publications are not reproducible. So the estimate is about half of all publications in history are not actually based on a scientific method. And now you can see sort of even the basics of sort of what is truth is being questioned and so on. So that is not a sustainable development. This cannot go on, so of course. This threatens the sort of fabric of modern society. And Ottersen, the president of the finest institution in Sweden, Karolinska Institute, is highlighting this. We are in the midst of a reproducibility crisis, and then left unchecked, this troubling fact may threaten our ability to generate sound, evidence-based knowledge that meets society's needs. And that was a few years ago, and now I would say sort of we are there, right? So this happened. So we need to resolve that. And a very pedagogic way to think about this is that in school, if you're in math class and you get sort of a problem, and then you say the answer is 2, then the teacher says you get 0 points, you have to sort of show your work. But in academia, this is not like that. You can just publish a paper, here is the answer. Then people say, how did you derive that? And then they say, I'm not going to tell you. So we're not even doing like elementary school standard, right? But it's a simple solution. So we present the digital math framework as sort of a robust foundation for that with FEniCS then, of course, as the key component. So basically, you can do to publish all the digital objects in a Jupyter notebook, in a sense, right? So then you can reproduce, you can run, and we call this a showcase as a modern scientific paper. So then you can think of this as this Jupyter notebook has all the elements. It has sort of a title, an introduction, references, and so on. But all the plots are sort of runnable. You can rerun, and you can also edit. And this is what we're leveraging also in the pedagogic setting. So for example, and I say CFD is easy, so and it's the same formulation for the aircraft. So basically in one line, so this is what I mean, this is like Newton's law, F equal to ma. That's it. You sort of, you type that or you modify something in there, in the web browser, and then you run interactively. And then another challenge, almost all students lose motivation for math and STEM by high school. This has been going on for maybe 30 years or something like that. So you could say almost no one in society is motivated by math or STEM, especially not the teachers maybe. So we present based on what I've described. You play with simulations. The DigiMat pedagogical or educational program. So it's a new revolutionary way to learn math plus coding. So in principle, for all levels. So at the high level, you play with FEniCS simulations, basically this Adaptive Euler and so on with FEniCS. But we also generalize this sort of for all levels. So basically you leverage the digital computer. So you can use very simple and powerful algorithms, time stepping, to simulate all of math and science. And here you can sort of see the first activity. You create your own, let's say, character or scenario, and then you press play. It does time stepping, and you start playing with the algorithm. And this is the pro. We can skip that. On the pro level, you do a similar thing with the Jupyter Notebook. A summary. So today we see large-scale threats to the scientific basis of modern society. So basically the concept of truth is under attack, right? But what we call this digital math framework, we see that as a counter, a robust scientific basis for research and education and industry. And then these three sort of, if you're mostly interested in CFD, then look into Adaptive Euler, sort of super simple, first principles, extremely fast and cheap, and what I've described here as well. Connected to Euler, I just want to show one pedagogic animation. So it's okay if it doesn't. So where was that? Here. So this is the basis for our breakthrough with Euler. So the sort of counter to Euler was that if you have a free slip condition, then you can construct a symmetric solution which has zero drag, like a cylinder, which satisfies the equations. But if you say Euler to people in the field, they usually think about like 2D stationary Euler, and then that can be true. You can have such a stable sort of symmetric solution. But in 3D time-dependent Euler, that solution is not stable. So it wants to sort of, it's unstable and wants to start to rotate. And then you get these sort of streamwise vortices. And that gives you an unsymmetric pressure, an unsymmetric solution, which has drag. And also for Euler, you can say one perspective is that the Euler represents a paradigm shift in fluid mechanics, giving a first principles approach and in principle resolving all the challenges in NASA vision. Sorry, I'm out of breath. And the second perspective is that the Euler approach is, you can see it as a wall model LES, where the model happens to be zero friction, but it's 1,000 times faster and cheaper than the sort of established approaches with a joint-based adaptive error control. So I'll stop there, and we can zoom into details if you're interested. Thank you.
Very much. We have time for maybe one or two quick questions. Going once, yes.
Yeah, I just didn't really understand why. I mean, Euler flow is inviscid flow, right? So you neglect the viscous part. Why is it more accurate and why is it faster than doing the full Navier-Stokes?
So the Navier-Stokes approach, then you have a no-slip condition. So you have zero velocity at the boundary, but then in the mean flow, it's high velocity. And with higher and higher Reynolds numbers, you can think of larger scales, larger velocities. You get sort of a higher and higher gradient going from zero to high velocity. So with Navier-Stokes, the approach is that you need enormous resolution. So the estimate is that you need to wait until year 2070. Then you can use Navier-Stokes for a full aircraft on the largest supercomputer on Earth. So you have to wait 50 years. But with Euler, you have a free slip condition, zero friction, so you don't have a gradient at the boundary. So that makes it possible to simulate today. So that is the breakthrough. So Navier-Stokes is simply not possible today, but Euler is sort of super cheap. It costs $1 today to do a simulation.
Go ahead, Joe.
Yes. Yes, so what I showed with the cylinder, you see the separation mechanism. And the main challenge of high lift is the angle of attack increases. You get sort of a large separated wake, which decreases lift. So, but that is sort of the same separation mechanism that you see on the cylinder, but it's just a complex geometry. So we also show, and you can see here in very high detail, sort of, here are the pressure cuts on different sections of the wing. And here, for example, is this large separated wake. So in a mean setting, we match the experiment very well. And you can see basically everywhere, we nailed the experiment with Euler's without a boundary layer and with like a mesh that is 100,000 vertices.
Thank you. I believe it's time. So let's thank all our speakers again.